So like I said, one way to describe this course would be a course of vector calculus. And so we better know about vectors. We better know about exactly what vectors are. So when talking about vectors, it's really in comparison to scalars. What's a vector quantity versus a scalar quantity? So do you guys know from other courses physics? What is a scalar quantity versus a vector quantity? Right? Yeah? And the other just has? Yeah, right. So they're both quantities. They both have numeric value, but then one has direction associated with it as well. And which is that? Vectors also have the direction associated with it. So you have a physical magnitude in both cases, and then vectors, in addition, have the direction. So scalars are just quantities. So what are some examples of scalars? Quantities, real-life quantities that don't have a direction associated. When I say direction, I mean like this way, or that way, or this way.
Yeah. Speed, but I also have a question. Is this also going to be online?
Yeah, so I will record all. I forgot to mention that. So so on Blackboard, you'll see. Oh, it's not there. There, right here under homework is going to be a link, lecture videos, and so everything I do will be on the screen, which is through my laptop. And so I'll take a screen recording on my laptop, and then the sound is the ambient sound in the classroom, which is my voice and your voices. So you get a full reproduction of class in the video. And so the links will be YouTube links that will give you a full video. Now, this is never a reason to not come to class. I'm going to be taking attendance starting Wednesday. When I put you to work, I'll have an attendance system on the screen. So you still got to come to class. What the videos are for is review and consolidation and reinforcement of the material. Okay, so a very common experience the students have is when they leave the classroom, they feel like, oh, I got 85, 90% of that. Really well, I got it, okay? But then 12 hours go by, and 24 hours go by, and you've had 3 more classes, and you played football, and you did your laundry, and you went to lunch, and hopefully dinner also, and all these things start tumbling out of your mind because it's the first time you ever saw it in class. So you may have understood it in class, but you've got to repeat it. You've got to repeat it, and that's what the videos are for, okay? So lecture video link here, we'll have the links to the YouTube videos, and we are recording right now. So yes, back and review this. All right, so he said speed. What's another example of a scalar? Something that doesn't have direction. Yeah. Age doesn't, that's right. Anything else you could think of? What's that? Any time quantity will not be a vector, it will be a scalar. Mass is another one, doesn't have direction. Distance, okay. Temperature, how about temperature? Yeah, so what else is there in there? So the quantities that have magnitude, not direction, that's temperature. Mass was said. Time elapsed. Volume is another one. Area, right? These don't have a direction in space, right? They just have a value, okay? Scalars. Okay, so vectors, what are some quantities that have an associated direction? Velocity, okay? Force is a good one. Acceleration. I was going to say that. Okay. So quantities that have a magnitude and associated direction. So force was said. Momentum is one. Okay, so now someone said distance for scalar, and that's correct. So the vector equivalent of distance, when you put distance along with direction, is called displacement. Displacement. So not only how far you go, but in what direction, right? So I'm going 3 meters that way. That's a vector then. And we call that a displacement vector. So just the quantity without the direction, as we mentioned, how far would be distance. So I want to make sure we have the terms down. When we say displacement, we're talking about how far along with in what direction. When we say just distance, we don't care about direction. It's just the how far part. Make sense? So then similarly, someone said velocity. Velocity would also be the vector. That would be the how fast along with in what direction. And so then just the how fast, no direction, is the term is speed. Okay, does that make sense? Questions on that? So vectors, huge. So we're going to talk about vectors most of the day today. So how do we represent vectors? When we draw them, represent them with arrows. So the direction, obviously, the direction of the arrow is pointing in the direction of that quantity. And then the length, if you have more than one vector shown at once, or if it's shown in coordinate plane, then the length refers to the magnitude of the vector. So which one of these has the greatest magnitude? Second one, obviously, and the least magnitude is the third one. Okay, so it's just we use length in drawing to kind of represent relatively the magnitude of the quantity. Okay, and so then we talk about the tip and the tail when we draw a vector. And so if it's a displacement vector, then the tail is kind of like the starting point, and the tip is then the ending point if it's a displacement vector. And then that kind of represents that change, right, in position. So displacement is like change in position from the tail to the tip. Now, if it's a velocity vector, we're really just considering the velocity here at the tail in that direction, and then this isn't like distance traveled, but how fast in that direction. So for a velocity vector, it's just really about the velocity at that point that we put the tail at. Okay? And then the length of it is how fast, and in that direction, obviously. Okay, so when we represent them symbolically, we use like in printed text, you'll see a bold letter. So like the bold V, that's a commonly representing, say, this vector. So we can't write in bold, so what we do is we'll just put a little arrow over it. So like this is the vector A, and you know it's a vector because it has a little arrow over the top. Okay. And in my PowerPoints, I'll be using that interchangeably. You'll see bold, you'll see the arrows over it, and when you're writing, obviously you want to use the arrow. Okay, so what does it mean for two vectors to be equal? Well, they're going to have the same direction and the same magnitude. If it's the same vector, it's got to have all qualities of the same. But not the same location. So vectors are not dependent on location. So for instance, so 5 people move starting at different places and times, but all go the exact same distance, heading in the exact same direction. So it's person 1, 2, 3, 4, 5, like a marching band, right? So are those different vectors or the same vector? They're all the same vector. Huge point. And this can, if you're just starting out with vectors, this can be a stumbling block. These are the exact same vector. They could all just be called D. Okay? Why? Because they have the same direction and the same magnitude. Where the tip or the tail is doesn't matter. Okay? So that's what makes vectors equal. All these vectors are equal. Okay, so how do you add vectors? So adding vectors, so here's 2 vectors. What would it mean to add them together? So the easiest way to think about adding vectors, maybe to start off, is like with displacement. So what we want to do is place the arrows tip to tail. So think about if you made the displacement of vector A first, and then the displacement of B, well, the tail of B B first. This is B plus A. This is B first, and then where you ended up after the result of vector B was where you want to start for vector A. And so then the result is what? The resulting vector is from where you started originally to where you ended up in the very end. So the sum is a single vector that results the same outcome as the original vectors applied in succession or applied together. If you applied both of those vectors together or in succession, what one vector would do all of that. Or another way to think of it is like, you know, the expression, as the crow flies, right? To get from one point to another, as the crow flies would just be from the start to the finish. So this is the vector B plus A. Does that make sense? So then what about the vector A plus B? So at first I do A, and then from the tip of A, I put the tail of B and do B. Then as the crow flies is that. And what do you notice? It's the same vector, right? Same vector. Remember, position, the The placement of the vector doesn't matter. Vectors are mobile. Vectors are mobile. As long, and these have the same direction and magnitude. So addition, vector addition, is what we call commutative. It doesn't matter the order in vector addition. You're going to get the same vector in the end. Okay, subtracting, a little bit less intuitive. All right, so to subtract vectors, so one way to think about it is you could add the opposite. So if I want to do b minus a, I could do b plus the opposite of a. And what is the opposite of a? Same magnitude, exactly in the opposite direction. So when you do the opposite of a vector, you don't change the magnitude, you're just going exactly the opposite direction. So what would it mean to add those two? So to add those two, we'd put it, again, tip to tail, and we do b plus the opposite of a, and then we'd get this one as the crow flies. So that would be b minus a. And that's great, you can use that, but when we represent subtracting vectors, here's where it gets a little tricky. We represent those tail to tail. Okay, so normally we would start off, instead of taking the opposite vector of the one you're subtracting and adding, we would start by showing them tail to tail. So the difference vector is going to complete that triangle, but then the question will be, which direction? Is it going to be up and to the left or down and to the right? Well, we already know the answer because we did it over here. But what if what if you don't do this first, right? So what if you want to be a little more efficient, a little faster? You put them tail to tail and you want to know. So is b minus a up that way, or is the tail here down, and is it pointing down this way? So there's different ways to think about this. So different ways to kind of solve that. So you can think about b minus a is kind of like final minus initial, right? Like, so the difference of two things is kind of like final minus initial, like the amount of change, right? Final minus initial. So that would indicate that your final is b. You're ending up here, and your initial is a. You're starting here. So that would be consistent with this going this way. All right. Another way is you can just try it both ways and see which way the addition works. So what would be true in this case? Would b plus b minus a equal a, or would a plus b minus a equal b? Looking at where the arrows are. So looking at this, the way it's configured here, which addition makes sense? B plus B minus A equals A, is that true? So you can do the math. B plus B minus A, does that equal A? No, you get like 2B minus A. Do you see that? Yeah, so it's like no, right? But instead, if you did A plus B minus A, right, you get A minus A is 0, and you're left with B. So then that makes sense in the picture too, because as our addition, A plus B minus A equals B. So I guess what I'm getting at is there's lots of ways to think about subtraction, and so you just kind of have to find the way that makes the most sense to you. So you might go through the video and think about that again. But basically, we want to put them tail to tail, and then we need to figure out which way does B minus A point. Does it point from that to that, or does it point from this to this? So you've got the algebraic check of addition. You've got this final minus initial kind of. Final is B, initial is A, so it's going to, final is at B, initial is at A. Both of those work. Any questions on subtraction? Okay, vector components. Okay, so how do we mathematically represent vectors? So what we do to kind of, in order to compare and combine vectors mathematically, we want to express them in terms of their horizontal and vertical components. So here's a vector U, which can be broken up into the sum of a horizontal part and a vertical part. So the horizontal part, or there's V too, the horizontal part of U is -1, strictly, so because it's pointing to the left, it's negative. And then the vertical part is +2. And by adding those two components, you see by our vector addition that you get the vector u. Right? So if you traverse that -1 across and then did 2 up, the result would be u. So we write it this way. So we use chevrons, okay? Chevrons, and in your web work, use a greater than and less than to make your chevrons when you put in vectors in web work, okay? So you're going to do greater than and then your components with comma and then your less than, right? First one less than. So less than and then your components and then greater than is what vector will understand as writing a vector that way. Okay, so here's a huge important thing. So looking at the vector u, we have these numbers, -1 and 2. What do those numbers mean for the vector u? This is huge. This is really important. You understand what vector components are signifying about the vector. So I want you to meet the person next to you and have a 30-second conversation. What do those numbers, what does -1 mean about the vector u? What does the number 2 mean about the vector u? Okay. So what do we come up with? What do you think? Somebody new. I actually heard the key word over here to my right. Someone said it. Yeah.
Like the change in or change in the independent versus the change in the dependent.
Okay, so we don't necessarily have.
Okay.
Yeah, so we don't necessarily have. It's not like a function like a y is the function of x necessarily, but you got the key word. -1 is what? Is the amount of change in this case x or in the horizontal. It's the amount of change, okay? And 2 then is the vertical change of this vector. Okay, so it's not wrong to actually maybe say this if we're thinking about calculus. That wouldn't be wrong to say that vector components are like dx, dy, or delta x, delta y. So huge. These are amounts of change in the respective direction, either horizontal or vertical. Okay, and so for v, we've got the vector v is 4, -2. So what's really powerful about this is now when we want to add, subtract, there's different kinds of multiplications of vectors, we have apples to apples, right? Because u and v are pointing in different directions. Numerically, how do you add them? You can't because they're in different directions. But if you isolate their horizontal components, well, those now you have apples to apples, and you can combine those. And if you isolate their vertical components, again, apples to apples. So, or oranges to oranges, right? So before we add u and v together, let's talk about another way to represent the components, and that's what's called this standard basis vectors. So in terms of horizontal components of vectors, kind of the key root vector is this vector I. And what are the components of that? How would you write that as components? 1, 0, right? That would be 1, 0. And so we can get all horizontal components as a kind of a scalar multiple of this, right? And then j would be the vector 0, 1. So then by scaling I and j, we can get the vector u. What would we have to do to I and j and combine them to get the vector u? So we just take the opposite of I, and we take what? 2 times j, and if we add them together, we'd have the vector u. So it provides a different way of expressing the vector u. So this is like component form. Oh, what happened? So there's component form. That's just the, like I said, with the chevrons, right? The negative 1, 2. And then there's the getting caught up. Here we go. So there's component form. Blow this time. Here we go. Component form. And then standard unit basis form. Or standard basis form. These both express the exact same thing as the sum of a linear combination. So it's a linear combination of our I and j vectors, or just straight off the components. So sometimes WebWork will have you be entering vectors this way, sometimes this way. And you'll see it interchangeably on in my PowerPoints, in texts. You'll see it both ways. Yes, please.
Are I and j universally remembered as those vectors, or is that just being used?
Yeah, it's pretty universal. I've never seen it different anywhere else. So that's a pretty universal thing. It's as universal as x is the horizontal axis and y is the vertical axis, which you can change. You can do it differently, but you hardly ever see it, right? Okay, so now adding them together, what do? If I want v plus u, I put the tail of u on the tip of v. So remember, vectors are mobile. I can just slide that thing down and it's still the vector u. And now we can just, to add v plus u, what can we do? Simply add so the result of v plus u would be, v gave us 4 horizontally to the right, and u took us back 1 horizontally to the right. So then the horizontal component of v plus u will be 3. And then v took us down 2, and u took us back up 2, 0, right? So this is the beauty of components. You can just add horizontal and vertical components because they're the same quantity, right? They're the same quantity. And we get 3, 0. And that agrees with the vector that we're seeing there. Has all horizontal change of 3 and no vertical change, right? 0 vertical change. So this is the unit basis way, right? 3i. So just 3 times that vector I. Don't need to add, we could say 0 plus 0j, but don't need to because it's just 0. All right, so remember that the length of the arrow represents the magnitude of the vector, so we want to find the magnitude of all three of these vectors. How would we find the magnitude of those vectors? Okay. How about v plus u? Let's do that first. What's v plus u? What's that? To represent the magnitude of a vector, you'll see single bars, like absolute value. You'll also see double bars. It means the exact same thing. Whether you see a single bar or double bars, in both cases, it means just the magnitude of the vector, or how long is the arrow? How long is the arrow? Or what's the magnitude of the quantity? Okay, so what about v plus u? If you understand vectors, there's nothing to do, because it's just, we know that it's a change of 3 in the horizontal direction, no change in y, so it's just simply 3. Just write it down. Now the others, how are we going to find the magnitude of that? How are we going to find the magnitude of that? Or, in other words, the length of that vector.
Square the x, square the y.
Yeah, so if you know what those components mean, right? So what do the components mean? I'm going to put it down here instead, so I'll make the -2 first. So that's -2j, right? And this is 4i, right? How long is that? 2, right? The magnitude of that vector is 2. That one's 4. And we know that as horizontal and vertical components, those are at a right angle. And we get a triangle, right? So what is the magnitude of v then? Square root of -2, or 2 squared plus 4 squared. Okay, so then we could come up with a general magnitude formula, right? So for some vector dx dy. So if vector v was just generically dx dy, how would you write the magnitude of vector v? Everyone do it. So what would the magnitude of vector v be? Again, single bars, double bars, same thing. Somebody knew? How would I calculate the magnitude of v then? Yeah. Square root of the horizontal component squared. And where's this coming from? This is just the Pythagorean theorem, right? Just solving for the hypotenuse in the Pythagorean theorem. Sum of the squares of the legs, square root. Questions on magnitudes of vectors? Important. Okay. Find and sketch v minus u and find its magnitude. Quick. Can you do quick? So make a sketch of v minus u. And again, do it in your sketch. Put v and u tail to tail. Put v and u tail to tail, and then determine what v minus u is. The question is v minus u, does it point down and to the right, or does it point up and to the left? So somehow you have to have some scheme to figure out that that would point down and to the right. And you can check that by this. So u, right, algebraically, u plus v minus u should be v, right? So if this is going to be hard to draw, I'll do my best. It's the best hard vector I've drawn all day. All right, so v minus u. So in the configuration, u plus v minus u equals v. And does the algebra work out? U minus u is 0, and we're left with v. All right, and then just doing the math is super easy, right? Because you got 4, negative 2, and then minus negative 1, 2. So we just subtract components. So we get x component is 5. Y component is negative 4. Does that agree with our picture? Positive x component, negative y component. So 5, negative 4. Any questions on that? Okay, so what would 1/4 v be? So let's just talk about 1/4 v. What would the direction of 1/4 v be? Same as v, right? What about the magnitude? 1/4 is long. So this is called scalar multiplication. 1/4 v would be the vector 1, right? Negative a half. So we call it scalar multiplication because it just takes the same vector, it holds its direction, and it scales it. So in this case, it scales it to 1/4 of what it was before. Does that make sense? So then what about 2u? What does that do? Doubles what? Magnitude. And what about the direction? Still points up and to the left at that inclination, right? And then multiplying by 2 just doubles the magnitude, so it doubles the magnitude of each component. So does scalar multiplication always preserve the direction? When doesn't it? Right, if you multiply by a negative scalar, then it will do what to the direction? Just flip it exactly opposite direction. So it will scale it by the amount, whatever multiplying factor you're multiplying. But then if it's a negative, it will take the opposite. We saw that before with the, we saw it earlier. But so negative 3v will take the magnitude of v and increase it by a magnitude of 3 times, but then we'll point the opposite direction. So then this sum of these two vectors is simply the sum of these components. So what you get? Negative 1, 7/2 would be that. So this is called scale. Each of these individual little things that we did here, 1/4 v, 2u, called scalar multiplication of vectors. So you're just scaling the vectors, changing their magnitude by a scaling factor, and then keeping the direction or going the opposite direction if it's a negative scalar. All right, so initial and terminal points. So if I was at point P was 1, 2, and point Q was 4, 1. Now, are these vector components? No, these are locations in the plane, right? So a point, if you have parentheses and you're just locating a point in the plane. Although coordinates do mean a change. What is the change of 1? What change of 1 is there to get to point P? From the origin, right? So these are changes from the origin. When you have coordinates, those are actually changes from the origin, right? You're going to go 1 across and 2 up from the origin. 4 across and 1 up from the origin to get a location. So now if we want the vector PQ, so that now is the vector with tail at P, right? So the P is right below the tail of my little arrow there. Q is below the tip. So this is the vector from P to Q. And we know that's going to have a horizontal change from P to Q and the vertical change from P to Q. So what's a horizontal change from P to Q? 3. And? -1. So in general, how would you calculate that change if you knew the position of the endpoints? So that's going to be what? X final minus X initial, right? Vector components give the change, right? So this is going to be the horizontal position final minus the horizontal position initial gives you the amount of change horizontally. Same with the y's. So what would the vector QP be then? It's a different vector. So now our horizontal change is -3, vertical change is +1. So it's just going to be the opposite of these components because your horizontal component is the other direction. The amount of the change is in the other direction, and the same with the y. Okay, questions on that's a crash course in vectors, and you'll get lots of practice in the web work. So the other thing I want to, any questions? Yes, please. 11:15 a.m. So WebWorks always do 11:15 before class. All right, so now I want to introduce you to another important thing. And that is so up to this point in your algebra and calculus career, you've lived here, right? The Cartesian plane, or the XY plane, or rectangular coordinates, or R2. Why is it called R2? Okay, dimensions. Well, what's the R? What do you mean by R? Right. So if we're really so it's like this is like how you'll see it, but I'll write just R2. It means the same thing, right? So we have the real numbers horizontally, all the real numbers horizontally, and we have all the real numbers vertically, and so this is the idea of R2. So Calc 3 is all about R3. Three-dimensional space. Where are you? No, I guess I can't move around. Okay. That's pretty good. Okay, so we've got three axes now, and this is drawn to trick your eyes, right? To make it look like a three-dimensional situation on a two-dimensional plane. So this axis right here is really coming straight out of the screen at you, right? And this is pointing to the right, and this is pointing up. So this isn't pointing down and to the left. It's, you imagine this is coming straight out of the screen. This axis, you imagine is coming straight out this way. Does it make sense? Okay. So you might think, since we have our x and R2, x and y, is like this is x and this is y. Not the case. Here's how we do it. So I'm going to, watch me. I'm going to grab hold of this. I'm going to take it. First I'm going to turn it like this. So now I'm looking at the xy plane. And now I'm going to take it and I'm going to turn it down like this and put it flat on the ground. One more time. Ready? Grabbing it off the screen. I'm going to turn it this way. Here's my x-axis. Here's my y-axis. And now I'm going to just totally screw that up. No, that's right. Yeah, that's right. That's right. And then I'm going to turn it down like this. So now the axis coming out at you is the x, and that one's y. That was perfect. I didn't screw that up at all. Just tricked myself. So this is x, and this is y, and when we look at this xy plane, we have to imagine this xy plane that we've been working at for 10 and 15 and 20 years, okay? 15, okay? So it truly will be. I mean, we'll when we're doing things in R3, we will often be imagining this xy plane and drawing it like this, and doing things in xy, drawing points and lines and vectors and different things, and having those be correspondingly in the horizontal plane here. Okay, so then this makes this our z-axis. So if I've got the point 3, 4, 2, that's x, y, and z. So 3 is x. So we start from the origin, and which way are we going to go? Out the screen towards you, 3 units. So 1, 2, 3. There's x equals 3. And then I'm going to go up, down, left, or right? Right. The y-axis is going to be positive 4. So if you see, I've got the tick marks here. A little hard to see. So starting from there, 2, 3, so I'm not going to go, so here's y equals 4, but I'm not going to go straight down like this. So I'm going to kind of maintain the parallel to the x-axis like this, right? So this is coming straight out of the board at y equals 4. So then 3, 4. So that's the 1, 2, 3. I travel across to y equals 4, and then from there I go up 2. Now it's not going to be at this height on your page. It's going to be up 2 from here. So 1, 2, maybe something like that. So now to help you see it, you can draw like a box, right? So 1, 2, 3. So when you're first dealing with these, the R3 plane, or the R3 space, I recommend that you draw a box. So from here we go up 2, just like from the origin we go up 2. We can kind of connect that. So I kind of missed here. It should be there. Trial and error is kind of the name of the game here. All right, so that kind of helps you see the point, what, 3, 4, 2. All right, so the horizontal plane we already talked about is the XY plane. How far is that point from the XY plane? How far is that point from the XY plane? You should see it's 2 units away. How far is that point from the XZ plane? That's the vertical plane that comes through and cuts through the screen like this. How far is that point from the XZ plane? 4 units. And finally, the plane of the screen is which plane? The YZ plane is the plane of the screen, and that point is how far from the YZ? 3 units away from the YZ plane. And if you want to know how far that was away from, say, the x-axis, do you see it would be this distance right here? That distance right there, that straight line from that point to there, would be the distance to the x-axis. And I'm sure you can figure that out. Okay. Happy web work. See you.